Hello and welcome to another episode of Effective JaRu, the series where we will read effective Java and try to port the items over to idiomatic Rust if possible. So in the previous session, we have implemented a planet enumeration, and I expressed my doubt that this is a good design for a planet. I mean, it's a planet, right? So we just took it as we just took part to show how it would look, even though I don't think it's very practical to have that. Maybe to finish it up, it's quite interesting to see that these are more like statically initialized constants, right? This is what happens here, and this is how it looks like. So it's really very, very different from an enumeration in Rust. So the next one is the operation here. Let's see how that looks like. So an operation, is there anything I skipped? Yes, this is what I skipped. So here we basically have an operation enum that is able to apply itself. Well, it can compute the result of the operation between two operands. And he says very soon, look at this, by the way, here. There's a switch case, right? And he says that this switch case is a problem because it's non-exhaustive. Whereas the code is fragile. If you add a new enum constant, but forget to add the corresponding case to switch, then it will still compile, but fail at runtime. Yes. I mean, instead of a default case, there's an assertion error thrown here. In order to protect against that case, that's a good thing. Yet there's no compiler telling you. So switch is inherently unable to have exhaustive cases. So it's a switch, right? It's not a match. So there's this workaround here that is also shown here. So you have basically an in-place concrete implementation of this enumeration, which implements the abstract apply function that is defined in the body of the operation, which is quite an interesting thing to do. This is really like a subtype. I would wonder how this is implemented internally, but this looks like it's a subclass of operation that is initialized statically with a little bit of extras, like the values method that exists on that exists on operation here, or in every enum for that matter. So that is a totally different way to deal with that. It's really more like a bit like a fake. However, in order to not forget to implement this, the abstract method here forces you to actually implement apply in the right manner. This is, as usual, I'd say, in the Java world, very redundant. The good thing is that it indeed works. If you would add a new enum variant, then you would be forced to implement apply, because this kind of is a subclass of the operation, which is abstract now, or has abstract members that want implementation. So there's also I think toString. What's the string to enum? No, it's a parse implementation. So from string implementation that just makes a lookup. It just makes a lookup here in a hash map that is statically generated. So you iterate the values that you have and create a map of basically a reverse mapping, right? You convert this to a string, and this value is then the statically initialized instance of the respective variant. I think that's how that works. And it's in a way it's nice because you don't have to deal with that anymore. But in another way, of course, it's quite wasteful, right? You have a static hash map again is all. I mean, sure, you don't have to bother about heap You don't have to bother about heap allocation because in Java that is the thing to do. There's nothing else really. So yeah, let's not deal with that. In Rust, obviously, this would be a bit more. It would be a bit different. So maybe, yeah, I kind of would like to restructure this so that we have a clear space, because there will be payroll as well. So let's have a module planet, and then we pull in planet here to make it work as it worked previously. That's kind of the standard to do anyway. It could be, I don't know, I think mods come below or something, besides the fact that we obviously right now don't have that module. So let's quickly create it. Planet.rs. There we go. And that should be all we need to make this work as it worked before. Cargo test. No. Oh, it's a pub use here, of course. We have to re-export it. And maybe it's the wrong way around. I don't know if the order matters. Anyway. Ah, I know. I think, I always forget this. Excuse me. So this is mod planet, that's for sure. If we managed to do this correctly here. Yes. But then it might be this to make it work or something. Oh man, come on. This usually is easy. Planet. Oh, I was looking at the wrong thing. Because this fails. Yeah, let's quickly fix this. Come on. This is now self planet. Right now that we are a submodule, we have to do it like this. That's always something that I mess up. So you cannot just copy this when you import your enumeration members. Yeah, easily forgotten. But good, now it works. I don't know what's a good order here. I think first defining the modules and then doing the rest is fine. So we have a new operation. Let's put in the file. It's op.rs. So we pull it in, and then we pub use op operation that shall be defined in a moment. Unit. We will see if we need any unit tests. Right now everything is implemented using using an actual program, but it's good. I will be happily removing that. So let's do it. Pub enum operation. And yeah, again, we are not constants really, so we just say plus, minus, times, divide. And now it's about the implementation. As ref we need, let's do it right away. Impl as ref str for operation. Fn as ref. So we convert ourselves into a string slice. In order to do that, we just have an exhaustive match on ourselves. Maybe we also use ourselves, use self operation, everything, so that we don't have to type so much. So this shall be what? This shall be a plus, minus, times. What about multiplication and division or something? Addition, subtraction, yeah, that's the terms I would use. But in order to keep it a bit closer to the original, let's just go with that. Divide is that. Cool, so now we have our conversion to a string slice. It's highly efficient, no memory allocated, it's all static data basically. And then we also want to implement parse, we want to implement from string. And I'm wondering, is this part of the prelude? Import from string for operation. Apparently not. So let's bring it in. Use std string from like this. Damn it. So what's the inverse operation? From str. It's an std str. Sure. It's not a it's just a string slice that we are talking about. From str. So I wasn't too wrong here. And I think we need to provide a result type. So after all, because we have a custom error type here. So type error is, yeah, what kind of error do we want to provide? Let's just put in a string here, which is a bad, not a terribly bad habit, but usually as an error type, you should also implement the error trait. You should. Doesn't really matter if you don't do it because people see what kind of error type you have anyway. So right now I would just say I provide a formatted string that says what works and what doesn't work. So fn from str, I guess we get a string as input, as we do, and we put out a result with an operation. So that's the type, obviously, that is us, that we implemented for, so it's self. And the error type is self error. That's it. It's the same as we do here, and I would like to keep it symbolic. We could also use explicit types here, obviously, but for the most part. So we match on the string, and now we can actually match on what it is. And this shall be a plus. This shall be a minus, and this shall be a times, and last but not least, this shall be a divide. Thank you. So that should be a valid implementation. Now we can parse ourselves. And sure, we are not exhaustive, mind you, because the string could have any amount of stuff. So we have a default case, which is that. And now I can just, oh yeah, by the way, it's an OK here that we provide. Let me think. Yeah, what we can do is here we do an early return and then put in some formatting saying that this is not a valid operation. And then we just drop in the string here. Good. And in the other case, we just wrap the result here into an OK. And this, I think, keeps it clean. The OK, of course, is the positive part. And this one here does an early return, so that doesn't affect the actual return type or whatever we return here. So yeah, that is that. That's how I would do it. It's quite, slim. Not too much code for what you actually do with full error handling and stuff. So that looks good. So now we have implemented quite a lot. Last but not least, the apply method that we want. And so far we've been implementing traits. Now we finally implement the operation itself, fn apply. We could be a bit more generic here, but to keep it simple, I guess we just go with f64. How it's called, x and y. X f64, y f64, and we return an f64. Good, and once again a switch. So it's x plus y. Oh yes, and what about a instance here? This would have been a static method, which is not so useful in our case. But, can be done. Static methods are usually, static methods are usually used as constructors, obviously. So x minus y, x times y, and x by y. Good. So that's the implementation. It seems to be complete. Let's use it. Oh yeah, it should be a public one, huh? Pub of n. Let's have another executable. Source bin, how is it called here? Calc. Let's call it calc.rs. It's a very cheap calculator. Once again, we need to get some arguments, and yeah, we might as well we might as well do it as they do. So like throw exceptions if something doesn't work, even though that's not usually the Rust way, especially if you see code like this that says let x f64 be, yeah, let's get the args here. Env args skip 1. Interesting that apparently now I get it. The args, they don't contain the executable file. Probably in Java it doesn't make so much sense because it's always some class path that is provided that is always Java. Kind of makes sense, but in Rust it's just standard C basically. So yeah, here we have an iterator, and we could say args next. Could be an optional, we just expect it to be there. We could at least be nice and say first argument must be the first operand. And then we do the parsing. This time I'd say, we don't do anything. Parse by don't do anything except for unwrapping. Parse, by the way, is implemented in terms of from str. This is how that works. So parse is just a convenience method basically on the on a string slice, or on a string for that reason. So let y be f64 args. One more, please. Expect second argument must be the second operand. Okay, and now we parse and unwrap. Whenever you see an unwrap, your program can just abort with a panic, so you probably shouldn't do it. And now you go through all the operations again for op-in, which is something we cannot safely do, so we don't have values. Safely in the sense of we might miss an operation here. So that's something you don't want to do, or you might want to maintain elsewhere maybe. Yeah, but in any case, it's dangerous. So, sure. What about the operation extern create item 30, use item 30. How do I call it? Oh, it's just operation, sure. Operation this. So we make it short and spicy. Like that, I guess. And now let's do it. It's plus in order of definition. That's how the Java version works. Minus times divide. And now we just print the stuff, huh? Is all right. So x op as ref, not to forget, because we didn't implement toString or anything, or not toString, display. It's a very important difference, because toString allocates a new string, whereas display writes something into a formatter which can have any backend. So this could also go to std out, for instance, which is what happens here. So we don't have intermediate memory allocations. It's really great to have control over that. So y and then equals, so op apply xy, right? That is all we need. So let's see if that compiles. Cargo build. Nearly. Unresolved import. Operation extern create. Oh yeah, typo. Excuse me. 2 typos in one word. Cool, now it worked. Now we can try to run it. Run bin calc. And it says first argument must be the first operand. Sorry. So foo obviously doesn't cut it. We just get a parse float error. That's good. Kind invalid. I mean, it's, you know, rough, obviously, but we are still better than the Java version without any more effort or so. So I think it's good. And consider how easy it is. You know, we always use parse. We don't have to think about it. There's no parse double, parse float, parse everything. It's really generalized, and that's so amazing. So let's take 1 and 2 and see. 1 plus 2 is 3. 1 minus 2 is minus 1. 1 times 2 is 2, and 1 by 2 is 2. I think that thing actually works. That's nice. Let's try the Java version. So it's item 30, and then it's operation 1, 2. Yeah, interesting. It has a different default print mode. I'd say I prefer the one Rust provides us because it's more readable out of the box. Very nice. But yeah, that is that. Really simple. That's an operation. And yeah, what else can I say? I think it's clearer regarding the code. And also it's definitely safe because of the exhaustive matches. So I totally preferred this over that anytime. But hey, that's just my opinion. I think the payroll example we do in the next session. Thanks for watching and have a great day.